Join us as we unravel one of the most revolutionary theories in physics, Einstein's theory of relativity. Einstein's theory of relativity changed our understanding of space, time, and the universe it's. Einstein actually developed two theories of relativity, each revolutionary in its own way. Special Relativity, published in 1905, deals with objects moving at constant speeds, especially near the speed of light. General Relativity, published in 1915, explains gravity as the curvature of spacetime it's. These two theories form the foundation of modern physics and our understanding of the cosmos. Special relativity starts with a simple but profound observation about light. The speed of light in vacuum is always the same, about 300 million meters per second, no matter how fast you're moving. This constant speed, denoted by c, is approximately 300 million meters per second. Whether you're standing still or moving at high speed, light always passes you at exactly the same speed. One consequence of constant light speed is that time itself must be flexible. If you travel at high speeds, time actually passes more slowly for you compared to someone standing still. This equation shows how time changes with velocity. Delta t prime is the time for a moving observer, while delta t is for a stationary one. The moving clock ticks slower than the stationary one. This isn't an illusion, it's a real physical effect. Perhaps the most famous equation in physics comes from special relativity. Energy equals mass times the speed of light squared. This elegant equation reveals a profound truth. Mass and energy are actually two forms of the same thing. Mass can be converted into energy and vice versa. A tiny amount of mass can be converted into enormous amounts of energy, as demonstrated in nuclear reactions. This principle explains how nuclear power plants work and why the sun can shine for billions of years. General relativity takes these ideas even further with a radical new view of gravity. Einstein showed that gravity isn't a force pulling objects together, but rather the curvature of spacetime it's. Massive objects like the sun create curves in spacetime, and other objects follow these curves, which we perceive as gravity. This is Einstein's field equation. It describes how matter and energy curve spacetime. Einstein's theories make predictions we can actually measure and observe. GPS satellites experience time differently than we do on Earth's surface, and this must be corrected for accurate positioning. Light from distant stars bends as it passes near the sun, exactly as Einstein predicted. Massive objects bend the path of light traveling near them, an effect called gravitational lensing. General relativity predicts black holes, regions of spacetime so curved that not even light can escape. Understanding relativity is crucial for modern technology and our view of the universe. Relativity is essential for GPS technology, nuclear energy, understanding space travel, and theories about the universe's origin. Einstein showed that space and time are not separate entities, but are woven together into a four-dimensional fabric called spacetime. Relativity fundamentally changed our understanding of reality, showing that time, space, and gravity are far stranger than common sense suggests. Let's review the key insights from Einstein's revolutionary theory. Space and time are relative and depend on the observer's motion, not fixed and absolute as Newton thought. The speed of light is the ultimate speed limit of the universe, and nothing with mass can reach or exceed it. Mass and energy are interchangeable, related by the famous equation E equals mc squared. Gravity isn't a force, but the result of massive objects curving the fabric of spacetime around them.